Hello everybody. In this video, we will cover the notebook for stabilizing facial landmarks. Now, if you use facial landmark detection on a single image, it looks fine. However, when we try to use it on a video sequence, there is no guarantee that the exact same location will be identified in each frame. And because facial landmark detection is done on each frame independently, there is no connection between two frames. As a result, you may see that the points jiggle a little bit. There is a little bit of jitter when you see the points, especially if you keep the face static. In that case, you will notice that these points start jiggling a little bit. So when the motion is small, it is really pronounced because that small error, which should be near zero, actually shows up. When the motion is large, you do not see the jiggling of the landmarks as much. Now let's look at the information we need to perform the stabilization. First, we need the location of a landmark in the current frame. We need the location of the same landmark in the previous frame. And we need small windows around the landmarks. We need the pixel intensities in these small windows around the landmark in the current frame and in the previous frame. These methods that we are going to cover, they are general purpose. They can be used to track points in general. They are not related to facial landmarks in particular. So whenever you want to track points in an image, you can use some of these techniques. The first method is to use a simple moving average. What it means is that over the last few frames, you know the location of a particular landmark in each frame. So we can perform a smoothing over time so that the jitter is gone. For example, if you're looking at the current location of a landmark, you can replace this current location by a moving average of the 5 last frames. So you calculate the average of all x and y coordinates in the last 5 frames and you replace the current estimate by that value. Now you can also do a weighted average. You could say that you have more trust in the current location and you give it a higher weight. And as you move to the second, third, fourth, and fifth frame, the weights you give to those locations is less. But the idea of using this moving average is that it will eliminate jitters. It will make the motion smooth at the expense of a little bit of accuracy because you're doing this smoothing. Now, the second option is to use Kalman filtering. We are not going to go into Kalman filtering in this course, but if you have taken course 1, we explained how Kalman filtering can be used to model the location and the physics of motion, as well as take into account the uncertainty in various estimates. So Kalman filtering, if you do not know about Kalman filtering, look it up. It is a very useful technique. But in this video, we are going to cover optical flow-based image stabilization. The reason is that in optical flow-based image stabilization, we can also use pixel intensities to guide us to find the location, to stabilize the landmark points. Now, optical flow was also covered in the previous course, but in case you have not taken course 1, let's go over optical flow briefly here and see what we want to achieve. Now, one way to think about stabilizing landmarks is to think about it as tracking. If you think about the problem of stabilizing landmarks, it is the same problem as finding the location of a point in the next frame, given the location of the point in the current frame. So it is a tracking problem. If you're able to track the point from one frame to the other, you have essentially stabilized it, because then you won't see it jittering. You won't have to rely on detection to locate that point. So now we are going to show you a method called optical flow, which allows you to track a point from one frame to the other, given the location of the point in one frame and the pixel intensities in that frame, and the location of the same point we want to find in the next frame, given only the pixel intensities. So the input is, we have the previous frame and the current frame, and we have the location of the pixel in the previous frame. We want to find the location of that pixel in the current frame. So let's see, we have a point x comma y in the image at frame t. In the next frame, which is given by t plus dt, the landmark moves to the point x plus dx and y plus dy, where dx and dy are small displacements in the x and y direction. Optical flow is basically the velocity of this pixel at this frame. So if you want to find the velocity, is nothing but dx by dt and dy by dt. So you want to find the u and v velocity in the x and y direction. So you want to find the velocity u in the x direction and the velocity v in the y direction. And if we are able to calculate this, we are able to track the point, because we know the original location of the point. We can multiply u times delta t and find the new location in the x direction. Similarly, we can find the new location in the y direction. There are two kinds of optical flow. One of them is called the dense optical flow, and the other one is called sparse optical flow. In dense optical flow, we calculate the optical flow at each and every pixel of the image. In case of sparse optical flow, we calculate some interesting feature points and calculate the optical flow only on those feature points. And since we are going to use stabilization for landmark detection, in this case, we are going to use sparse optical flow. In particular, we are going to find the optical flow for the 68 points that are detected as part of facial landmark detection. As you can imagine, there are several methods for calculating the optical flow. We are going to use the Lucas-Kanade optical flow algorithm. Now let's understand what's going on. We are not going to go over the derivation for Lucas-Kanade optical flow, but let me remind you that when we write the optical flow equation and try to solve it, it is an ill-posed problem, which means that there are two unknowns, u and v, but there is only one equation that relates these unknowns. So what do? Well, we have to make some assumptions when we want to solve such problems. And in Lucas-Kanade optical flow, the assumption that we make is that in a small window centered around the feature point, the optical flow is the same for all pixels. Now we have multiple pixels which have the same flow, which means that there are 9 equations and 2 unknowns, and therefore the system can be solved. So there is one equation per pixel. If you're using a 3 by 3 window, there are 9 equations, and we are assuming that the u and v components of velocity are the same in this small neighborhood. It's not a bad assumption. It's a very reasonable assumption to say that pixels are moving together, and we can use the information in these 9 pixels to calculate the u and v components of velocity. And turns out the solution offered by Lucas-Kanade optical flow is this equation. It may look a little bit scary, but it is not very scary. If you look at Ix, this is basically the gradient in the x direction. If you remember, we calculate the gradient in the x direction by running the Sobel operator on the image, by convolving the image with the Sobel operator in the x direction. And similarly, we find the y gradient by running the Sobel operator in the y direction. So we can find Ix and Iy. Now, how do we calculate It? It is essentially the difference between the current frame and the previous frame. So it is the pixel intensity difference. You just subtract the current frame from the previous frame and you get It. Expression wise, this is what it means, but I just told you how to calculate those things. So you get 3 images, Ix, Iy, and It, and therefore you can calculate u and v at whatever pixels you want. The optical flow equation works when the motion is sub-pixel. If it is more than 1 pixel, it breaks down. So how do we actually use it? Because most of the time, we do not expect the motion between frames to be sub-pixel. Well, in that case, we build image pyramids. So we take the large image, blur and subsample it again and again. So we have a pyramid of images we calculate the optical flow at the lowest resolution. Here we can assume that, okay, we have subsampled the image so many times that the motion is actually sub-pixel. It is not more than 1 pixel. And once you calculate the motion at the lowest resolution, you can use that information to calculate the motion at a higher resolution, and you can keep estimating the motion at higher and higher resolution, and thereby finding the actual motion. Now, even with this technique, there is a chance that the motion is very large and we don't get sub-pixel motion even at the lowest resolution. Well, in that case, we lose track of the point. So Gaussian pyramids are used to calculate the optical flow at low resolution and transform it and figure out the optical flow at higher resolutions. However, they are not guaranteed to work when the motion is extremely large. So what do? Well, we have to combine detection with tracking. So we cannot rely on tracking all the time. We have to combine some way of detecting the landmarks. Fortunately for us, in facial landmark detection, it is very fast and we can detect the landmarks on every frame if necessary. Now the question is, we have two estimates. We have an estimate of facial landmarks based on tracking, and we have another estimate of facial landmarks based on detection. Which one do we trust? Turns out that tracking does an excellent job when the motion is small. So as we had noticed that when the motion is sub-pixel or a few pixels, in that case, optical flow will do an excellent job. On the other hand, detection will give you a rough estimate of the landmark points, but it will not be consistent with the previous landmarks you detected in the previous frames. So that's nice. Detection gives you a rough estimate and tracking gives you a very precise estimate. So we can use tracking when the motion is small, and we can switch over to detection when the motion is large, because detection will work even when the motion is large. It doesn't know, it starts from scratch. However, we cannot make this hard switch. We cannot say that, oh, we are going to use detection when the motion is above a certain threshold, and we are going to use tracking when the motion is below a certain threshold. The reason is that if you take that kind of approach, you will notice large jumps between frames, which is not good. So we need to come up with a soft way of combining the two estimates. For example, we can choose an alpha which combines the two estimates. When the alpha is 0.5, it means that we are giving equal weight to both the estimates. And when alpha is, say, 0, in that case, we fully trust the position given by the landmark detector. And when alpha is 1, we fully trust the prediction given by the optical flow. The question is, how do we calculate alpha? We can calculate alpha by checking how fast the point is moving. In other words, we want alpha to depend on the distance between the location of the point in the current frame and the location of the point in the previous frame. And this distance is basically given by, this norm. If you want to expand this, let's say you have x1, y1 as the current estimate and x0, y0 as the previous estimate, then this distance is nothing but x1 minus x0 squared plus y1 minus y0 squared, and then you take a square root. So that is the distance between the points. Now the distance can go from 0 to infinity, and that doesn't get us alpha. So we have to map this distance to a number between 0 and 1. We can do this by using this formula. What we have done here is we are saying alpha equals e to the power minus distance squared by sigma squared. And the notion of distance is controlled by this parameter sigma squared. So this is used to normalize the distance. Now, this is a very standard trick in machine learning. Whenever we have something that goes from 0 to infinite and we want to map it from 0 to 1, then we use an exponential function like this to map it from 0 to 1. You can see that when the distance is 0, alpha equals 1. When the distance is infinite, in that case, alpha equals 0. This is a very standard trick. We have also introduced this parameter that controls the notion of distance. So in this particular example, we have made sigma proportional to distance between the corners of the eyes. So that way, this distance is normalized. In the face, the distance between the corner of the eyes is a very stable quantity. It doesn't change a lot between different people. So we can use that as a scale for the face. We could have used other notions of distances as well. For example, we could have used the size of the face bounding box to normalize this, but we chose to use the distance between the eyes. And both are valid ways. We just need some way to normalize this distance. Now let's see how this is done in code. We will need Lucas-Kanade optical flow that is implemented in OpenCV to perform this operation. And this is the function calc optical flow pyrlk that implements Lucas-Kanade optical flow in OpenCV. What does it mean? Here, calc optical flow is calculate optical flow. PYR stands for pyramid and LK stands for Lucas-Kanade. The important inputs are basically the previous image, the next image. These are essentially 2 consecutive frames of a video, and the previous set of points that you want to calculate optical flow on in the previous frame. And the output is the next frame and the status. Whenever the status is 0, it means that the tracking failed. It doesn't have enough confidence on the track point. So we can ignore tracking when the status is 0. There's another function that will come in handy as well, which is called build optical flow pyramid. We know that if we want to calculate the optical flow when the motion is more than subpixel, we have to build a pyramid. Now, we can pass the original images to optical flow and it will calculate the pyramid for you and return the optical flow. However, that is wasteful when we are processing a video. And the reason is that when we are processing a video, we calculate the optical flow pyramid for a single frame twice if we do it naively. When we want to calculate the optical flow for the current frame, we need the pyramid. And when we want to calculate the optical flow for the next frame, we will calculate the pyramid again. And that is completely unnecessary. We can calculate the pyramid once and then pass it to calc optical flow pyrlk. If you notice this carefully, it says that this previous image can be an 8-bit input image, or it could be a pyramid which is constructed using build optical flow pyramid. So we are going to use build optical flow pyramid to build a pyramid and pass it to calc optical flow so that we do not spend a lot of time in building pyramids. It is more efficient to build the pyramid once and store it for the next frame. So now let's look at the code. We start with our standard imports, including dlib. We set up matplotlib, and then we have the path to the shape predictor. And the size that we are going to use is 480 because the processing will be faster that way. We are going to calculate the frames per second, and for that we are going to use 100 frames to calculate what is the FPS. And we are not going to skip any frame. And for face detection, we are going to skip 1 frame. Now in this function, we are calculating the inter-eye distance. We are calculating the left corner of the left eye, the right corner of the right eye, and we are finding the distance. This distance will be used to normalize all distances in the image. So next, we go over a video file. We are capturing the video file. If it doesn't load, then we will just exit. For Lucas-Kanade optical flow, we need the window size, which we have set to 101. This is the number of levels of the pyramid. We have a maximum of 10 levels. So at each level, we downsample the image, and it can go up to 10 levels depending on the size of the image. The frames per second, this is just a placeholder. We are going to calculate it. Next, we are reading a frame and we convert it to grayscale. Before we move forward, I want to emphasize that optical flow methods are designed for grayscale images and videos because we care only about the intensity of pixels. So we have to convert the images to grayscale before calculating the optical flow. So every frame is converted to grayscale, and then we set up our detector. This is the face detector. We also set up the landmark detector. We will first detect the face, and inside the face, we are going to detect the landmarks. And we have initialized some parameters here, the points, which is the points in the current frame, the points in the previous frame, and we have the detected points in the current frame and the detected points in the previous frame. These points would capture the points detected by the DLibs facial landmark detector, and these would be the estimates that we finally have after stabilization. These are some variables we use to check if we have already calculated the distance between the eyes. If we have, then we don't need to calculate it again. We do some processing when we recognize it as the first frame, and that is why we are using this variable. And our interface allows you to toggle between showing detection results and stabilization results. So this variable controls whether we want to show the detection results or the stabilization results. Now, this is the main piece of code, but before we jump into the code, I want to summarize what we are going to do. First, we are going to detect the face at a lower resolution, and we'll get a bounding box. We will resize the bounding box so that it is at the highest resolution. And then we are going to get two estimates of the location of the landmarks. One using detection, we will run the facial landmark detector on the current frame to get an estimate. And then we will also get an estimate for the location of facial landmarks in the current frame using optical flow. So we have two estimates, and then we need to combine these two estimates. To combine these two estimates, we will calculate alpha, which will provide a linear combination of these two estimates. And alpha will be based on how fast the object is moving. If we detect that the object is moving very fast, in that case, more weight will be given to facial landmark detector. If the object is not moving as fast, in that case, more weight will be given to the optical flow estimate. So that is it. Let's see how it is done. In this piece of code, we are simply doing some resizing, etc., making things ready. And here we run the detector only once in a while, and we run it on the small sized image. You can see that we have resized the image so that we can run the face detector on a smaller sized image, and we are also skipping frames to make things faster. Now, if there are no faces, then we just go along. But if we find faces, in that case, we get a new rectangle from the face detector. This new rectangle needs to be resized because we had detected the face at a lower resolution. So we are resizing it using IMResize to get the rectangle for the highest resolution image. Next, we are running the landmark detector and getting all the landmarks. Now, the first frame needs to be treated slightly differently because in the first frame, we do not have a previous frame. We cannot do optical flow. So if it is the first frame, we simply put the points previous and points detected previous. Both of them are populated with whatever landmarks we have received. But if that is not the case, we copy it from the current estimate of points, and the current detected points are also copied over to points detected previous. And then we have to populate points and points detected current. So if you look at it, we are working with two variables. One is points previous and the other one is points current. And this is the points previous, which is after optical flow. This is points detected previous. This is the result of landmark detection in the previous frame. Points is the points that we are going to finally output. This will be the current points after correcting for optical flow, etc. And points detected current is basically the output of the landmark detector on the current frame. So that is what we do. We populate both points detected current and points with the current landmark location. Now this thing is going to change because we are going to use optical flow to modify these points. These points will not change. They will have the location of current landmarks as detected by the landmark detector. Next, we convert it into arrays for floating point arrays. And some of these conversions are happening because the function that we are going to use, the input they take is in a specific format. So we need to sometimes convert it from float to int, etc. Now, we want to do this processing at a particular scale. We need to know what kind of windows we are going to use for optical flow, etc. For that, we need to find what is the size of the head. Now, we could use the size of the detected face, but that is more noisy than finding the distance between the eyes. The distance between the eyes is a very good measure of the size of the face. And that's why we are finding the distance between the eyes. It will be used to calculate a lot of things. For example, here we use the distance of the eyes to find the radius of the dot that we are going to display in our final display. The landmarks would be displayed using a dot. If the face is large, in that case, the size of the dot would be large. Otherwise, the size of the dot would be small. We are also going to use it to calculate sigma that we are going to use to divide the distance measures. When we see the motion of a particular landmark between two frames, let's say it has moved from location 0 to location 100 in the x direction. Now, these are 100 pixels. We don't have a sense of what this means. I mean, 100 pixels means very different things based on the scale of the face. If the scale is large, 100 pixels could mean nothing. It could be very small motion. But if the face is very small, 100 pixels is a very large motion. Therefore, we have to normalize this motion based on the size of the face. And that is what we are doing here. We are going to use sigma to normalize the distances. And this sigma is calculated based on the distance between the eyes. We are also calculating S, which is window size of optical flow. And here we are setting up the parameters for Lucas-Canade optical flow. The window size is dependent on the distance between the eyes. The maximum level is the maximum number of resizing we do. Criteria is the termination criteria. This is very common in many iterative algorithms. We have to tell when the algorithm should stop. And usually we use two termination criteria together because one of them may take a very long time. In this case, we are using two termination criteria. The first one is called term criteria count, which means that after applying 20 iterations, so this one is 20, after applying 20 iterations, stop, even if the required accuracy is not met, because we have to stop after some time, otherwise these things can go for a very long time. The other termination criteria is based on accuracy or convergence. Suppose we are trying to minimize an objective function and that function is not changing anymore, or when we are converging to the final value, we are saying that when those values do not change anymore or the EPS is small, then stop. So those are the two criteria. We say that either you hit a fixed number of iterations or you hit a certain level of accuracy. In both cases, terminate. So that is what is going on here. Next, we pass the optical flow parameters to calc optical flow PYR LK and calculate the points through optical flow. So these are the new points that have been obtained using optical flow. Now, there are a few format conversion transformations we need to do here. This is just because the data needs to be in a certain format. So nothing substantial going on here. Next, we need to calculate the alpha, which will be used to combine the detection and optical flow results. Let's see how it is done. So in this for loop, we go over all the landmarks and then we calculate the distance of that landmark from the previous position to the new position. This is the position in the previous frame, and this is the position in the new frame. We calculate the distance, d. This distance is from 0 to infinity. We need to convert it from 0 to 1 because alpha needs to be between 0 and 1. So here we are doing e to the power d squared by sigma. Sigma provides the normalization we need, and d is the distance. Now e to the power anything, especially with a negative, goes from 0 to 1. When d is 0, then this number is 1. When d is infinite or very large, then this number alpha is almost 0. So we are combining the points now. The first set of points is points detected current. So these are the points that were detected by the landmark detector, and these were the points that were estimated using optical flow. And based on alpha, we are combining the two. Again, when the alpha is small, it means that the points are not moving that much. In that case, optical flow results will be better, and therefore this thing goes up when alpha is more. And alpha is high when the distance is small. Okay. So now we have stabilized points. These are essentially stabilized points. Now we just need to display these stabilized points. And if we have turned on this variable, in that case, we display the stabilized points. If this variable is false, in that case, we display the detected points. This way you can toggle back and forth and see how the results are. We also set the first frame to false, increase the count. The count is used to calculate the frames per second. So in this piece of code, that is exactly what we are doing. We are calculating the FPS. And the rest of the code is simply displaying the results. So that is it for this video. But before we go, I want to summarize the process one last time. Now, to detect landmarks in a frame of a video, we have two options. The first option is to use the facial landmark detector and detect the landmark points in the current frame. The second option is to use optical flow and the previous frame points and estimate the location of landmark points. So we have two estimates. Now we want to combine these two estimates to get a more stable estimate. How do we do that? We know that when the motion is large, we should be using the facial landmark detector output. When the motion is small, optical flow gives better results. So we come up with a mechanism of combining these two estimates to get a more stable estimate based on what was the motion of the landmark point between the frames. And that is it. Thank you so much.